Alright, we're going to take a look at the kinematics of circular motion. So we want to talk about how do we know when an object is accelerating. And if we take a look at the formula, right, the acceleration is a change in velocity over a change in time, or Vf minus Vi over t. So in order for an object to accelerate, obviously the velocity has to change. There's two ways that can happen. Up till now, mostly, we have dealt with where, there we go, change in magnitude happens. Right? So we speed up, we slow down, but the direction doesn't. But there's another way. We can keep the same magnitude, the same number, and if we change direction, acceleration has happened because velocity has changed. Alright, so let's take a couple looks at this here. Change in magnitude, this is what we've been doing, right? If we have acceleration to the right, we start with a slower speed to the right, and we continue to accelerate, and our Vf is going to be increased. If we have acceleration to the left, we're going to slow down our speed as we move to the right. Alright, so those are kind of the review ones. We've done and dealt with those already. The other kind is when we have a change in direction. And this is where the acceleration is actually it comes linked right away with a force. Because in this case, the acceleration is basically pulling our object around the corner. And the acceleration is always pointing towards the center of the radius, I should say the center of this circle, and we call this centripetal acceleration. In this section, we're going to look at motion that stays at a constant speed but changes in direction. We call it uniform circular motion. Right. So, if we look at some review again, it's just we're applying it now to a circle. If we have an object moving in a circle of radius r at a constant speed v, how do we determine its speed? Well, our original formula, v equals d over t, but, so speed, remember, is a scalar, so we don't have to care about the direction. V is going to be the distance for one lap. Remember that the circumference is going to be the distance that it travels. Circumference is going to be equal to pi d. And remember that the diameter is 2 radii. So I can replace my d with 2r. And I end up with my formula, v equals distance for one lap, which is really just 2 pi r, divided by t. Now in this case, it's time for one lap. We give that a special name. It's the period of revolution. Right, and that's a circular motion term that we use is t for a time for one lap or one time around the circle or one orbit if we're dealing with gravitational and planetary motion. All right. So when we talk about circular motion, the velocity is going to change. And this is only because even though the speed is the same, you'll notice our speed vectors, the purple things, are the same length. They're just continually pointing in different directions. And the direction is always in a tangent to the circle. So if, however we have this going on, the object was let go, it would now travel in the direction of the velocity along a tangential path to the circle, based on Newton's first law. Right? Due to inertia, an object in motion will remain at a constant velocity, same speed, and same direction, unless it's acted on by another force. Right? And so if we remove whatever's in the middle, pulling it towards the middle, it's going to just keep on going in a straight line. All right, so think discus, right? We spin around, and again, we're trying to draw this three-dimensional vector on a two-dimensional picture, but whatever direction that arm is pointing, the disk is going to travel away from this guy's body at 90 degrees to that. Right? Or if we're playing fast pitch, this ball is going to leave the hand at 90 degrees to the motion. Right? Or 90 degrees to the arm's direction. Baseball as well. Right? If the pitcher held on to the ball until it was pointing directly at the batter, the ball would end up in the ground, in the dirt, quite close in front of the pitcher. Same thing if we go back to our fastball pitcher. If she holds onto the ball, this is already follow through happening here. If she holds onto the ball till it's pointing exactly where she wants it to go, it's going to end up going nice and straight up in the air and not doing a whole lot of good to trying to strike anybody out. Right? Now, we are going to look at centripetal acceleration here, which is the acceleration when an object's velocity changes direction. We're going to analyze its magnitude and its direction separately. So first of all, the direction. This is actually sort of easy. It's always towards the center, and it's always perpendicular to the velocity. And you might ask, well, why is that? Well, let's imagine what would happen if it was not directed towards the center. So the little blue arrows here, this is where it actually is, but let's imagine it's this vector here. All right? Well, to analyze this now, we're going to break it into its vector components. Right? We break this into, we're going to call this an X and a Y component. Now, we've got a problem already. The X component is in the opposite direction of the velocity. This is going to slow it down, and now we're not going to have uniform circular motion anymore. Which means it's going to gradually slow down more and more and more. Or if it's somehow our velocity is in front, well then our X component is in the same direction as the velocity, and we're going to speed it up. So in this case, we are having circular motion, but it is not going to be uniform circular motion. So we keep it where centripetal acceleration is always directed towards the middle, always at 90 degrees, which means the X component is always 0, which means it does not change the magnitude of the velocity. All right, so a couple equations here we should look at. First of all, this is the one on your formula sheet, where the centripetal acceleration is equal to the circular speed divided by the radius of the circle. So meters per second and meters. Look here, this is sort of how we get to our units of meters per second squared, right? We have meters squared per second squared divided by meters, which works out to meters squared times meters divided by meters seconds squared. One of the meters cancels out. We're left with meters per second squared. All right, so a couple things here. My arrows somehow got goofed up. These should be a bit different than they are, but life goes on. So assuming speed remains constant, one of the things we should see here is that there is an inverse relationship with the radius. So our centripetal acceleration is proportional to 1 over r, which means if radius is multiplied by 3, the centripetal acceleration is multiplied by 1/3. This, I think, should sort of make sense. When the radius is large, the velocity changes direction slowly. Right? When the radius is small, the velocity changes direction quickly. Which means a smaller number on the bottom of our fraction means a bigger centripetal acceleration. Centripetal acceleration has a direct square relationship with speed. So if our speed is multiplied by 4, our centripetal acceleration is multiplied by 4 squared, or by 16. So again, when the speed is slow, the velocity changes direction slowly. When the speed is fast, the velocity changes direction very quickly. And again, so in terms of the change of direction, that's the centripetal acceleration part. All right. So, second formula here, right? If we start with this formula up here, and we look back at when we came up with the equation v is equal to 2 pi r over t, right? That was our original equation for the speed of this thing. I can take this v here, and replace it with this here. And so that's what happens right here. So AC is equal to 2 pi r over t, that stuff squared, divided by the radius. So let's expand this stuff out. And we're left with 2 squared is 4, pi squared is pi squared, r squared is r squared, t becomes t squared, all divided by r. Right? Now we can rearrange this a little bit. Take this stuff here, this r at the bottom becomes a 1 over r. And we multiply this all through. What we're going to notice, of course, let's get rid of my writing so I can add some new writing, is we have an r on the bottom and an r squared on the top. That means this, subtract 1 here, and this just goes away. And so now we're left with 4 pi squared r over t squared. And that's equal to our centripetal acceleration. So depending on what information we're given, we're either going to use this formula or this one. And both of them are given on your data sheet. Right. So when you have speed type information, we use this one. When we have period information or the time for one lap, we use this one. All right. So looking at this here, if we look if we're in uniform circular motion, velocity vectors are this way, and the acceleration vector is always towards the center. Right. Okay, this is just a little bit of a goofy, weird bit here, but what if you're given revolutions per minute? So in this case, it's going to be, let's say you have 850 RPMs. What does this mean? Well, remember the period is equal to the time divided by the number of cycles. So in this case, 850 revolutions per minute, 850 RPM, sorry, is 850 revolutions per minute, which means that the period is going to be, the total time is 60 seconds, that's the minute bit, divided by 850 revolutions, which means each one revolution takes 0.0705 seconds, or 7.06 times 10 to the negative 2 seconds. Which makes sense. If something is spinning 850 times in a minute, it means that each spin is not going to take all that much time. Come on, there we go. Another one here. Centrifuge spins at 20,000 RPMs. If the particles in a test tube experience a centripetal acceleration of 1.18 times 10 to the 6 meters per second squared, determine the diameter of their path. Right, so a couple things here. First, settle down. First of all, we want diameter, not radius, so we're going to solve eventually for radius, but then multiply by 2 to get diameter. Second thing, what are we given? Well, we're given centripetal acceleration, and we're given something that has to do with the period. So in this case here, our period is equal to the time divided by the number of cycles, 60 seconds divided by 20,000 revolutions, which means each one takes 3 times 10 to the negative 3 seconds. Starting with our formula here, we're going to rearrange this to solve for r. So we're going to divide both sides here by 4 pi squared and multiply both sides by t squared. And we are left with radius is equal to centripetal acceleration times t squared divided by 4 pi squared. And we take our information here, plug it in, and we get a diameter, a radius, I apologize, of 0.269 meters. Multiply by 2 to get to diameter. And our diameter is going to be 0.538 meters or 53.8 centimeters. And that takes us to the end right now.